Okay, we're going to pick back up. This is the, I think, seventh video now, but this is part two of how the periodic table uh, reflects this theory, the orbital theory that we covered in the earlier videos. Okay, I think I left off with beryllium as I'm filling up the periodic table. So beryllium again had 4 electrons, and those 4 electrons are all going to go into the lowest energy orbitals possible. So the first 2 of beryllium's electrons are going to go into the 1s orbital, which is the lowest orbital. And again, one will be positive spin, the other will be negative spin. And then the next 2 will go into the next highest energy level, which is the 2s. And again, the first one goes in positive spin, the next one goes in with a negative spin. Okay. Now, though, when we encounter boron, boron has 5 electrons. Well, where are they going to go? Well, they can't go into these orbitals because those are already filled. You can only have 2 electrons per orbital. So it's got to now go into the next highest orbital. Well, the next highest orbital from an energy standpoint, it turns out, happens to be the 2p orbital. Now, if you remember, 2p stands for L equals 1 from a quantum number, right? And so the 2p actually has n equals 2, L equals 1, and m equals -1, 0, and 1. 3 values. That's why we have 3 circles here. Okay? Because for the 2p orbital, there are actually 3 bubbles, 3 separate orbitals. Remember, even from a shape standpoint, one of them is shaped along the x-axis, the other is shaped along the y-axis, and the other is shaped along the z-axis. Okay? Each of them can hold 2 electrons. So now boron, with its 5th electron, is going to go and fill up one of those p orbitals with a positive spin. Okay? Carbon, when it comes around, it's going to do the exact same thing. Carbon has 6 electrons. They're going to go 1, 2, 3, 4, 5 like this, and then the 6th one like this. By the way, that's a rule, and again, it's kind of one of these math rules, but it also kind of bears out in the model, is that when an electron goes into an orbital or to an energy level that has multiple orbitals, that the successive electrons actually go and fill the next possible orbital. They don't, for example, do that. I think it's called Hund's rule. Okay, so they fill this way, 1 and then 2. So that's carbon. Okay. Similarly, nitrogen, it's going to be the exact same scenario, but now the 7th electron of nitrogen is going to go here. Okay. So nitrogen have 3 electrons at the 2p level, 1 in each orbital. Then we go to oxygen. Oxygen needs to add an electron. It's actually going to come and join one of the other orbitals that already had 1 electron, and it will join it with the opposite spin. That's oxygen. Fluorine will do the same thing with the 2nd orbital. And then neon finally completes the 2p orbital level. So now all of the 3 distinct 2p orbitals are filled once we get to neon. Okay? Now, again, it's interesting because whenever we end up with this, okay, now it's all filled, that usually indicates an element that is not very reactive, meaning it's very stable, has a very stable electron configuration, which again kind of makes sense when you think about it even at the electron level. All right, now, let's go on. So after neon, which is atomic number 10, atomic number 11 is sodium. All right, well, where's sodium's? Sodium's going to follow the exact same thing. It's going to go 1. It's got 11, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all like neon. And now it has an 11th. Okay, so where is that going to go? What orbital? Well, is there a 2d? Well, I don't think so. 2d would be n equals 2 and L equals 2. Now that's impossible. Can't happen because remember L can only be 0 and 1 for n equals 2. So there is no such thing as a 2d orbital. So it basically means we got to go to the 3 level, and it turns out the next highest orbital from an energy standpoint is 3s. Okay, 3s is a little bit higher than 2p, which was a little bit higher than 2s, which is higher than 1s. So again, when you look at an element and you look at all of its electrons, the electrons are all going to start by filling in the lowest energy levels. So when we talk about sodium at 11, it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's sodium. Okay. Magnesium, the next one over, it has 12 electrons, so it has just one more electron. It then is going to fill this orbital, the 3s orbital, because that's the lowest energy orbital, and there's still room for one electron. Okay. After magnesium, though, is aluminum. So where's aluminum going to go? Well, we have 3s, so it's going to go into the next highest orbital, which is either going to be 3p or 3d. Right? Because remember, at n equals 3, L can be 0, 1, or 2, meaning at n equals 3, you can have an s, a p, and a d orbital. Okay, but the aluminum's next electron, or extra electron, is going to go into the lowest energy one, and it turns out the lowest energy orbital available at this point is the 3p. And remember, 3p has 3. Not the 3d. 3d is a higher energy level, so we're not going to fill the 3d orbital yet. We're going to fill the 3p one, because the 3p is lower in energy than 3d. Okay, so aluminum, extra one will go there. Silicon, add it on. We're going to follow just like we did before. Phosphorus will be there. Sulfur will fill one of those orbitals. Chlorine will fill the second. And then finally we get to argon, we fill the third. Okay? So when we get to argon, which is again a nice stable noble gas, we've essentially placed our electrons in all these of these different orbitals. And again, back to shape, you can almost even try to picture that you've got these spherical shapes that start with really close to the nucleus, and then a little bit further away from the nucleus, and then a little bit further away from the nucleus. They're all spherical in probability density shape. They're all completely filled for argon. And then at 2p, you've got those barbell-looking things in the x direction, the y direction, and the z direction, all filled at the 2p level, and even all filled at the 3p level, which is just kind of a bigger version of those same loops. Okay, so that's what happens when we get to argon. All right, now we got to get to number 19. 19 is potassium. All right, potassium has got 18. It's got 19 electrons. So the first 18 are going to go just like argon. Where's the 19th going to go? Well, it's going to go into the next highest energy orbital after 3p. What's that? 3d? That'd be my guess, because d is higher energy than p. So it seems reasonable that 3d is the next orbital. Turns out it isn't. It turns out the next one up from an energy standpoint is 4s. 4s is slightly higher than 3p, but it's also slightly lower than 3d, and you'll see that in a second. Okay, so for potassium, which I'm going to draw way over here now. Well, actually, I'm going to draw it here because I'm going to keep it under sodium. But it turns out, as you can probably tell, it's probably a lousy spot for it, because potassium has 19, so we're going to put my electron there. And then after potassium, I want to say calcium. Yeah. The calcium has 20 electrons, so it's going to be 18, 19, 20. So now calcium has the 4s filled. Okay. And after calcium, now we've got scandium. Yeah, scandium. Okay, scandium is next. That has 21 electrons. Okay, so where the first 20 are going to go where we had them for calcium. But now the next one for scandium is going to go into the next lowest energy orbital, which happens to be, after 4s, the next lowest energy orbital happens to be 3d. I'm trying to draw these a little bit like this. Best I can, anyway. These are the discrete energy levels. Okay. So all I'm showing here is that 1s is lowest, then 2s, then 2p, then 3s, then 3p, then 4s, then finally 3d. If remember 3d, I'm definitely going to run. I'm going to erase this last row here. Just to make some more room. Okay, the next one is 3D, and I'm going to draw that here, 3D. And remember, 3D is basically n equals 3, L equals 2, and M can go from -2 to +2, so there's 5 values for M. Okay, so for 3D I'm going to draw 5 orbitals. Okay, scandium goes here. Then the next one is titanium, has 22 electrons. It's going to be exactly the same as scandium, but we have to add one more. Again, we're going to fill the next orbital up. Then we have vanadium. Then we have chromium. Then we have manganese. Okay. Then we have iron. Well, at this point now, iron's going to fill like this. Complete the first orbital. Then comes cobalt. Then comes nickel. Then comes copper. And then comes zinc. Not only do we get the zinc, zinc actually completes the 3D level, which is nice. So now when we go after zinc was atomic number 30, so 30 electrons. Now we finally get to gallium, which has 31 electrons. For gallium, gallium has to find the next highest energy level. Well, after 3D, it turns out the next highest level is 4p. So it goes 4s, then 3D is next in energy, then 4p. And remember, 4p has our 3 as usual. And so gallium is going to go into the first 4p orbital, then germanium, then is that arsenic? I think so. Yeah. Then selenium, then bromine, finally krypton. So krypton at atomic number 36 has completed all of these orbitals, the 1s, the 2s, the 2p, then the 3s, then the 3p, the 4s, the 3d. See, we're going backwards in number. That's because from an energy standpoint, 3d is higher than 4s. Then back to 4p, and now it's complete. So when we finally then go from krypton to the next, you'll see that we have to find the next orbital, which happens to be 5s. So a lot of this periodic table shape occurs due to the fact that the energy orbital, so the energy, each orbital has an energy state that is ascending kind of by n and by L, but there's some discontinuity in there as the L numbers get bigger. As you can see, when L gets to 2, which is the D, or when L is 3 for the F, those energy levels are higher, which gives rise to the strange shape of the periodic table. I think I'm just going to kind of end by, if you look at this, you'll see that well, actually in my next video I'll do one last one where I'm going to correct the shape of this thing and show how it relates to the S, the P, and the D orbitals.